and welcome to the second part of variable acceleration. So this is part 2. This is the second part of chapter 11. So let's have a go at some questions then. So we've looked at the fact that if we've got displacement, we can differentiate to get to velocity, we can differentiate again to get acceleration. But now what we're doing is we're going to be working backwards. So we're going to be integrating the acceleration to get the velocity and integrating the velocity to get the displacement. Now, with this one here, I'll show you that. I'll make this picture big for you so you can see it. So with this one here, remember that when we are integrating, you end up with that constant. Okay, so you end up with that plus c. Now, usually when we're doing these questions, it gives you an initial state. Okay, you'll notice, in fact, let's start this question here. I'm going to write down here, example 1. So I'll read it out. A particle is moving on the x-axis at time t is equal to 0. The particle is at a point where x is equal to 5. So that's the initial state that I was just talking about. The velocity of the particle at time t, where t is greater than 0, that makes sense because time is always positive, is 6t minus t squared meters per second squared. So that's the velocity. Find an expression for the displacement of the particle from 0 at time t seconds, and find the distance of the particle when it's from its starting point from when t is equal to 6. So let's have a little look at this then. So the first thing is probably worth writing down is what, because we know what that velocity is. The velocity is equal to 6t minus t squared. Okay, that's my velocity. Okay, it's asking for the displacement. So if I'm going from velocity to displacement, looking at this, the part above here, I know that I'm going to be integrating this. I'm going to be integrating v. So displacement is equal to the integral of v with respect to t. Okay, so s is equal to the integral of 6t minus t squared with respect to t. So I'm integrating this. So if I integrate this one here, 6t, it's going to be, you raise the power, divide by that power, so it's going to be 6t squared divided by 2. This one here, raise the power, divide by it, so it's going to be t cubed divided by 3, not forgetting to add c. Okay, this is the part you don't want to forget. So this isn't our final answer. What we're doing now is we are substituting in our values from our initial state, which said when t is equal to 0, x is equal to 5, my displacement is equal to 5. Okay, that's my initial state to find out what c is. It's probably worth cancelling this as well. So I end up with s is equal to 3t squared minus t cubed over 3 plus c. Let's sub in our value. So 5 is equal to 3 times by 0 squared minus 0 cubed over 3 plus c. So c is equal to 5. So our final solution for this is s is equal to 3t squared minus t cubed over 3 plus 5, and that's the final answer there. So that's part A. So part B says find the distance of the particle from its starting point when t is equal to 6. Now this second part isn't too hard. We're just substituting. If we want the distance, okay, from its starting point, it's going to be, we're subbing 6 into that. Let me write that down on here. So I've got s is equal to 3t squared minus t cubed over 3 plus 5. And part B, I'm substituting in that value here. So s is equal to 3 times by 6 squared minus 6 cubed divided by 3 plus 5. Let's use a calculator for that. Oops. So in the calculator, 3 times by 6 all squared minus fraction button 6 all cubed divided by 3 plus 5, which is equal to s is equal to 41 meters. So you might be tricked in thinking that this is the final answer, that S is equal to 34, but there's a little tiny trick in this. And the little tiny trick is that it says, find the distance of the particle from its starting point. So from its starting point, well, its starting point is equal to 5, okay? So what's the distance from 5 to 41? Very sneaky, that. So the final part of this is 41, take away 5, which is equal to 36 meters away from the start. That last little part is very sneaky, okay? 36 meters away from the start. Let's just check that. Brilliant. Brilliant. Make that big so you can see the answers. Super. Okay, so let's have a go at this next question. I'll make it big for you so you can see it. So, a particle travels in a straight line. After t seconds, its velocity is v. And it's given as v is equal to 5 minus 3t squared. Find the distance travelled by the particle in the third second of its motion. Now, this one here is not saying, let me just snap back. This one here is not saying find the distance travelled at t is equal to 3. It's saying find the distance travelled by the particle in the third second of its motion. Now this third second is a whole second up to 3. Okay, so it's between 2 and 3. So what we're doing here, what example is this now? It's example 2, sorry. So this is example 2. Now, it can be confusing, this. And again, I do think this is sneaky. So example 2. Because it says in the third second, and everybody, especially in kind of 6 or 7 months' time, when you come back to this, you might just go, oh, t is equal to 3. But it's not the case. It's the third second of motion. What you're doing here is you're integrating this between 2 and 3. So that's the third second of the motion. And you're integrating 5 minus 3t squared with respect to t. And remember, when we're integrating like this, you don't need c, because the c's will cancel out. So let's integrate this now. So it's going to be 5t minus 3t cubed over 3 between 3 and 2. That 3 is going to cancel. You end up with 5t minus t cubed between 3 and 2. Let's sub those values in. So 5 times 3 minus 3 cubed. Subtract, let's put that in a big bracket, subtract 5 times by 2 minus 2 cubed, like so. So let's put that into my calculator. It's a big old sum, this. So bracket 5 bracket 3 bracket minus 3 to the power of 3, close bracket, minus, open bracket, 5 times by 2, minus 2 to the power of 3, close that bracket. I end up with minus 14 meters. Now you might think to yourself, how am I getting minus 14 meters? Why is this negative? Now don't forget that this just means that it's below the curve. So it's an area below the curve that's minus 14, but it's asking for the distance travelled. So the distance travelled is equal to 14 meters. Okay? This negative just means that it's going the opposite direction of the positive direction of the displacement. So it's going the negative way. So don't worry too much about that. Okay, let's just check this answer. Brilliant. You see that they've drew this diagram as well. Distance travelled is 14. So one more example. I'll make this big for you to have a go at. You should be able to have a go at this one yourself. So have a go at this one first. A particle P moves On the positive x-axis, the velocity of p at time t seconds is equal to 2t squared minus 9t plus 4. When t is equal to 0, p is equal to 15 from the origin. Find the values of t when p is instantaneously at rest, the acceleration of p when t is equal to 5, and the total distance travelled between 0 and 5. So have a go at that now. Okay, so I am going to have a go at this question as well. So what are they giving us here? Let's just check. They're giving us, what example is this? Example 3. So they are giving us the velocity, which is equal to 2t squared minus 9t plus 4. They're giving us the initial state, which is when t is equal to 0. The displacement, t is equal to 0. P is 15 meters from the origin. So yes, so the displacement is equal to 15. Okay, that's my initial state. So find the values of t when p is instantaneously at rest. Well, if this is at rest, then we are finding out when this is equal to 0. So let's make that equal to 0 first. This is part A. So 0 is equal to 2t squared minus 9t plus 4. I'm going to put that straight into the calculator. Polynomial, degree 2. So 2t squared minus 9 plus 4 is equal to, so t is equal to 4 and t is equal to a half. The values of t when it's at rest. Now, I'll come back to it in a second actually. So let's have a look at part B. So part B says find the acceleration when t is equal to 5. Well, my acceleration, I know, is the differential of this. So acceleration is equal to dv by dt. Okay, so let's actually do that. dv is going to be equal to 4t minus 9 plus 4 is going to stay the same. And I want it when t is equal to, what do you want, 5? So let's sub in value 5 now. So a is equal to 4 times by 5 minus 9. 4 times by 5 is equal to 20 minus 9 is equal to 11 meters per second squared. Okay, brilliant. So that's that question done. Now the next part says, and this is the bit I paused on before because I knew that this part was coming up, the total distance travelled by p in the interval between 0 and 5. Okay, now the reason that I've paused there is I know that I need to integrate. Okay, I know that the distance between 0 and 5 is going to be the area under the curve. But the reason that I've paused is because these here are the two crossing points. This is when the velocity is equal to 0. So it's telling me above this is going to be a positive quadratic, so it is going to be a U shape. If I was to draw the velocity time graph of this, I know this part here I'm cutting at 4. I know that it's 0 at a half and at 4 here. So this looks like, I've not done this very well, this looks like this. Okay, this is what this graph looks like. And the reason that they have given you this is because they're expecting you to make a mistake. If you were to just put this last part straight into your calculator between 0 and 5, you are making a mistake. This part A is a hint to you. So they're giving you a hint. And because it wants it between 0 and 5, you've got to split this up into 3 parts. So, into between 0 and 0.5 is a positive distance. Okay. This part here, between a half and 4, is a negative distance, but it's still a distance travelled. And the last part, because it wants it between 4 and 5, is going to be this part here, which again is a positive distance. So you've got to find between 0 and 0.5, between 0.5 and 4, and between 4 and 5. I've got to find those three separate parts. Now, has it given it me... Oh, I don't need the initial state, do I? Because I'm going to be solving between these two boundaries. So I want to integrate between 0 and a half the velocity, which was equal to 2t squared minus 9t plus 4 with respect to t. I need to integrate between a half and between 4 this 2t squared minus 9t plus 4 with respect to t. But I've also got to integrate this last little part here. So where am I going to put this? I'm going to put this one up here, if that's okay though. So integrate between 4 and 5, 2t squared minus 9t plus 4 with respect to t. So I'm integrating. I've got three areas here. And the reason that you've got to split it up is because this is above the curve, this is below the curve, and this is above the curve again. So we know before we start that this answer is going to be positive, this answer is going to be negative, and this answer is going to be positive. So we need to ignore the fact that this one is negative and then add all of these together. Okay, I'm going to use the calculator for this, okay, because I know that I could integrate this, but if it's going to take a while, so let's use what we've got, and we will have this in the exam, so there's no worry about that. So integrate 2, it's going to be x, isn't it? 2x squared minus 9x plus 4 between 0.5 and 0. So that first one is, so this one here is equal to 0.9, no gravity involved, no, 958 meters. This one here should be negative. So integrate between 4 and 0.5. Yes, it is negative, thankfully. So minus 14.29. Okay, and this one here we know should be positive as well. So integrate between 5 and 4. That one is positive, brilliant. We're on to a winner here. 4.167. Probably should have done that to 3 decimal places. Anyway, negative, positive, negative, exactly as we described it. So we ignore the fact that that's negative. We've got 0.958 plus 14.29 plus 4.167. So that's all those areas. So 0.958 plus 14.29 plus 4.167 is equal to, let's do it to 19.4 meters in total. Brilliant. Let's check that we've got that right. Notice that was 5 marks. That should be the hint, okay, that there's a little bit more that you've got to do. Okay, so that is the main part of this. These are the kind of questions that tend to come up. There is another little part to do, which I'll do in a second, but what I would suggest is that you do have a go at this exercise here. Okay, there is a last little part which is on proof, but actually these are the type of questions that come up. It's also worth doing the mixed exercise, but I will do the last little part of this, which is just the proof of the formula, so constant acceleration, so we can actually prove these using differentiation and integration. So this is the last little part. So we've been using SUVAT to prove the formulas. It's also possible to derive all of these using integration, provided we consider that the acceleration is a constant. Okay, so given that a body has a constant acceleration of a, an initial velocity of u, and its initial displacement is equal to 0, prove that v is equal to u plus at and s is equal to ut plus a half at squared. So, the first thing that we are going to do is part A. We need to integrate A with respect to t, okay? We're integrating A with respect to t to get that velocity, okay? So if I integrate A with respect to t, okay, because I know that if I integrate t, I get the velocity, I end up with at, remember this is equal to the velocity, plus some value c, which I don't know, okay? If I integrate A, it's going to be, just a little side note, if I was to integrate x with respect, sorry, not x, if I integrate 3 with respect to x, that would be equal to 3x plus c. So if I integrate A with respect to t, that's equal to at plus c, okay? And I know that the velocity is equal to the integral of A. Now, I use these initial states to find out my formula. So it tells me that A is equal to my acceleration. It tells me that my initial velocity is equal to u. So that's my starting velocity. And so my t is equal to 0. And at that point also as well, s is equal to s. And the velocity is equal to u. So what it's telling me is when t is equal to 0, u is my starting velocity. So when t is equal to 0, my velocity is equal to u, which is my starting velocity. So if I sub those values in, u is equal to a times by 0 plus c. So I end up with c being equal to u. And then we've pretty much proved it, because if c is equal to u, my starting velocity, then I have v is equal to at plus u. Switch those round, v is equal to u plus at. Brilliant, and that's what we were looking for, using these states here. Now this doesn't come up very often, it's very rare this come up, but this do ask it every now and again. So it is worth having a look at this. So part B says, use the same states here to prove the formula for displacement, which is s equals ut plus a half at squared. So I know that displacement s is equal to the integral of v with respect to t. Okay, I know that my displacement s is the integral of v with respect to t. So s is equal to the integral of v, which is u plus at with respect to t. So if I integrate u with respect to t, I end up with ut. If I integrate at with respect to t, well, that's like saying 2t. That is a number, okay? So t, you raise the power and you divide by that. So it's going to be a raise the power on t and divide by that. It's going to be the half, isn't it? Plus the c. Brilliant. Let's write it in the way that we actually want it. S equals ut plus a half at squared plus c. I'm not quite finished just yet. Okay. It tells me that when t is equal to 0, my displacement is equal to, I put s up there. My displacement, is equal to 0. Okay. So when t is equal to 0, my displacement is also equal to 0. So I'm saying here, subbing into this, 0 is equal to u times by 0 plus a half times by a times by 0 plus c. So that's 0, that's 0. C is equal to 0 at the start. So I end up with the formula s equals ut plus a half at squared. And we've proved them. We've used the formulas, we've used our initial states to prove the Suvat equations. Now, as I said, that doesn't come up very often. The questions you want to focus on are these type of questions, because these do come up all the time. Okay? So, that is actually it for constant acceleration, okay, and variable acceleration. That is the end. What I would suggest that you do is you have a go, if you've not already, have a go at this chapter here. So page 189 to 191, but also make sure you have a go at the mixed exercise at the end. So maybe do all the even questions or maybe do all the odd questions. Make sure you're having a go at those. You know that you differentiate and integrate to get either you differentiate the displacement to get the velocity and acceleration, and you integrate the acceleration to get the velocity and the displacement. Okay, brilliant. Super. Well, thank you for watching part 2 of variable acceleration. Remember to make sure that you have a go at these questions, because the only way to learn maths is to do it, and have a lovely day.